Welcome to your first video of the MCPS Virtual Physical Science Learning Module. That is a lot to say. This is Module 1, Foundations of Physical Science. And in this first video, we're going to be learning about motion and forces. This video will provide you with an overview of the information that you'll need in order to move on and practice some of this stuff, apply the knowledge that you get here. There's going to be additional video resources at the end as well on the resource page that will help you to dive even deeper into some of the topics that I will go over in this video. So the first thing, of course, let's talk about motion and what this idea of motion is. And here we see this picture of a train shot flying through, and someone who came up with a lot of the ideas that we followed today about motion, his name is Sir Isaac Newton. And you've probably heard that name, that Newton name. It's not only a unit we use in physics, but this guy came up with the 3 laws of motion. All right, so we are going to take a look at the 3 laws of motion that Newton came up with. But before we jump out and define these laws, we're going to look at an example to help us just to see motion, and this is going to help us understand the first law that Newton created. All right, pennies stack up on this paper, and then we're going to flick it out and watch the pennies. They fall directly into the glass. So that quick video by Six Science really helps us to introduce this idea of motion. And how does that happen? We flick the paper out from underneath, the pennies fall directly into the glass. How does that work? Well, we can also, instead of using that example, we can look at this soccer ball. All right, the ball is at rest right now. Can it go into this goal by itself? Is it just going to just magically get there? Can it accelerate on its own? I mean, of course not. You're probably rolling your eyes being like, no. It requires someone coming in to kick it or push it or throw it or do something. Right? Well, this idea that someone needs to push or pull or move this ball, this is the definition of a force. Right? And a force is an interaction that causes an affected object, the soccer ball, to be pushed or pulled in a certain direction. Right? And this provides the basis of Newton's first law. And we'll get to balance and unbalanced force, but for now, just know that things at rest, here, an object at rest, will remain at rest unless a force acts upon that object. All right? And, of course, then, the other side of it, things in motion will stay in motion unless another force acts upon them. All right, so soccer ball at rest until someone kicks it. They kick it, it starts to move. If it's moving through midair, nothing's stopping it other than maybe air resistance. All right, it's going to keep going until, boom, it hits the back of the net, and therefore the motion of that ball will stop. Now, another word to describe all this is something called inertia. All right, and that's the tendency of all things to remain unchanged. This is the reason that while riding in a car, you feel a jerk when the car brakes, right? Your body wants to keep moving at the same speed that it's at. Even, going 60 miles an hour down 270, all right, your body is traveling that fast as well, not just the car. And there's many factors here because as you are now going forward, like almost slowing down, trying to get to rest, the car is still moving forward at the same speed. The seat is part of the car, right? Moving at the same velocity, and it's coming to then meet your body. And so you feel like this whole throw back and forth as the seat also begins to push on you. All right, so it's the same reason then that we have seatbelts, because if we don't have a seatbelt and we get into a high-speed accident like that car moving on 270, all right, that's how people are ejected from moving vehicles. Inertia. Object in motion will stay in motion unless acted upon by a force. So the seatbelt is that force holding the person back in a car. Now, this is also why the coin trick works. The coin is at rest on top of the paper. Even when the force upon the paper causes the paper to move out of the way, all right, it's not enough to move the coin in that forward direction. The coin stays at rest with no direct force on it until the paper is gone. And then there is a force, of course. Gravity takes over and the coin drops into the glass. These are great first examples to kind of start thinking intuitively about this idea of motion and inertia here from Newton's first law. All right, so Newton's first law, an object at rest will stay at rest unless acted upon by a force, and an object in motion will stay in motion unless acted upon by a force. And we got to stop and think how cool it is that this guy, Sir Isaac Newton, comes up with these laws of motion back in the 1600s, people. And now, several hundred years later, we are still following these laws and use them as the foundations of physics and motion. And I just think it's really cool. So, had to share that. Let's go on to Newton's second law now. And we can see that here, okay? It's all about the acceleration of objects, and that the acceleration is, of course, dependent upon the forces acting upon this said object, whatever it is, and the mass of this object. So we have two wagons here, wagon 1 and wagon 2. Now notice they both have the same amount of force being exerted on them. And we can see that here with those arrows. Notice they're the same shape and same direction, all right? When we see forces, we're going to use what's called vector quantities, okay? And hopefully you know something about vectors from math, all right? But a vector quantity in physics is, it involves the magnitude, okay? And magnitude is just the amount, right? The magnitude of the force, the size. This could be velocity. This could be, acceleration. This could be force. So the magnitude, and also we have to include direction with a vector here, okay, especially with motion. All right, so we see that the magnitude by the size of this arrow we're going to say is the same size, and direction also the same. It's going in the rightward direction. We have these right forces going onto this wagon. So same amount of force being exerted on them, okay? Wagon 1, however, has a smaller mass inside. So therefore, what do you think here? All right, we have the same force, lighter wagon. You imagine yourself pulling a wagon with this size mass versus this giant size mass. All right, which one's going to accelerate quicker? All right, well, of course, wagon 1, right? And you see that with this other arrow here in orange, the acceleration arrow, all right, is much, much bigger, all right, magnitude here than this acceleration arrow down here. All right, same direction, all right, but way different magnitudes here. All right, and that's because of the mass. It's all dependent on one another. All right, so the amount of mass and force is going to allow things to either accelerate quicker or slower, all right, depending on that mass. All right. Now we can get a mathematical look at this idea and these relationships between these variables with this equation here. And this is the equation that Newton's second law provides us. F equals ma. Get used to hearing that one. Force equals mass times acceleration. And the standard units are going to be used here for each of these variables. Force is measured in newtons. Hey, famous name. Mass is in kilograms. And acceleration will be in meters per second squared. Now, we have Newton's first two laws, just like the basic foundations here. So let's take a look at just general motion and see how we can connect all of this. So we will want to be able to use this equation at some point in this module. But we really need to understand this general motion, like I said, and this concept of acceleration. And before we get to acceleration, we got to even go a step before that, and that's just velocity. And what is velocity, and how can we use velocity, and in this case from a mathematical approach, to then visualize changes in acceleration and motion. So let's say we have constant motion going on, constant velocity, right? So we have a car, okay, and it's just going to draw a little graph here. Okay, and on the bottom axis we're going to have time. And so let's say at time 1, time 2, time 3. And we have a car that's going to be traveling at a constant velocity, right, of 10 meters per second. Okay, so get our units there. So this car is going to travel. All right, notice that graph, right? Constant velocity. There's no change. It's constantly at 10 meters per second. Whatever time you give me, if we keep going on this graph, it will be 10 meters per second. Okay, so what is the definition of velocity? Well, it's what distance was traveled in what amount of time, right? So we can now take a different look by, we're going to draw a new graph here. Let's get those axes. Okay. And let's say we put time again, all right, down here, but we're going to put our position or distance up on the y-axis, okay? And so we can mark out time 1, time 2, time 3, time 4, and our distances of 10, 20, 30, 40, right? And of course we could keep going up, 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 up. Well, let's go ahead and say that this car, we said its constant motion was at 10 meters per second to begin. So let's just start there. Things don't always have to start at zero. I know we're so used to things starting from the origin down here, but you don't always have to have that, especially in physics. A vehicle could be moving already at a certain speed or traveled a certain distance. So we're starting at 10, at the distance of 10 meters per second. The car is already out there. All right. So now, if we know that the car is moving at a constant speed, there's no acceleration, at time 1, how far has the car traveled? Well, if they're going 10 meters per second, in 1 second they're going to go another 10 meters, right? And then at time 2, they're going to go another 10 meters up to 30. And then at time 3, they're going to go another 10 meters up to 40. So now we have 4 points, and we can connect those and draw a line straight through them, and we see just a standard linear function here of these points. So why am I showing you this? Well, we can use the slope of this line, because what is the slope of the line here? Well, it's the change in distance, right, over the change in time, which means that we could just take, two y values, and two x values, and we could do the whole y2 minus y1 over x2 minus x1, and that's going to give us the slope of this line, which is equal to distance over time, which is equal to velocity. Okay, so at any point here, the slope of this line with here no acceleration, right? The slope of the line is equal to the car's velocity. And I could show you, 30 minus 20 is going to give us 10 for the y values, and 2 minus 1 is going to give us 1. 10 divided by 1, that's 10 meters per second. And that's exactly what we started with over here. That's what the velocity of this car. All right, so remember, slope of the line is going to equal the velocity, and we can use that as we now take a look at acceleration. The graph's going to look a little bit different, but we can still utilize this concept of slope equaling velocity. All right, so acceleration is in the mix. And if we wanted to look at a distance versus time graph of acceleration, right, distance versus time, let's say we had the same car, it started 10 meters out, all right, and at each given time it was moving, let's say, at an acceleration of 2 meters per second squared. So it's getting faster and faster. It could be traveling down a ramp. So this graph is not just going to be linear when you're looking at the distance versus time, right? Because the distance is going to exponentially increase as time moves on, right? Because it's moving faster and faster and faster and faster and faster. Okay, that's acceleration. However, we have this exponential graph. But what's cool about that is that at any given point on the graph, what does the slope of that line represent? Well, the slope of that line at any point, or we wanted to go up here and draw another point, the slope of that line at that given point is going to be the velocity of that car. And we can see it if we were to do a velocity versus time graph again. Velocity and time down here. Okay, we were starting at 10 meters per second. All right, time 1, time 2, time 3, time 4. Right, you're going to have 10 meters per second. Well, after 1 second, the car is now moving at 12 meters per second, right? Because it's increasing by 2 meters per second. So, boom, 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 and then 14, right? And then you can go up to 16. I'm not even going to draw it, but it would be up that way. And we see that when we look at velocity over time, even with acceleration in play, we can still get a linear graph, which again is just reinforcing this concept. Even when you have this distance versus time or this increase in velocity, at any point in time you can get the instantaneous velocity of an object by looking at the slope on a graphical representation of any problem you come across. So a quick review, we know now what a force is. It's an interaction that causes an affected object to be pushed or pulled in a certain direction. And we've seen Newton's first law, that an object at rest will remain at rest, an object in motion will remain in motion unless acted upon by a force. This brings up the concept of inertia, right? The tendency of matter to remain unchanged. We've seen some graphical representations of velocity, constant velocity, also with acceleration, how the slope of a line at a given point on a velocity graph or a distance first time or acceleration graph is going to show us the velocity. Slope equals the velocity. We've also seen Newton's second law and how that brings up the equation force equals mass times acceleration. And we are going to look at some applications of Newton's second law in the next video, and I'll see you there.